All right, we are on packet B and 4445. We're going to talk about mean value theorems for integrals. So this sort of piggybacks off of we did it earlier in the year on mean value theorems for derivatives, where then we talked about if you're driving from here to Florida and you're looking at your odometer and how long it takes you. So if your average speed on that filling up gas trip on that long journey, you're averaging 100 miles an hour. That means that at least one moment during that journey, you were traveling 100 miles an hour. And we talked about how that could be associated with toll booths and paying speeding fines and things like that. So it goes with that average speed. But now that we're talking about integrals, we're referring to area. So now we're kind of looking for that middle ground area. So we have the area from A to B here of our function. Okay, so then again, thinking of rectangles and going off of the Riemann sum concept, if we created one rectangle, and this is obviously an underestimate, but it's using that smallest value. So this is like the minimum area that you could have using the lowercase m, as opposed to the third picture, picking that maximum height and using that maximum area, which is clearly an overestimate. There has to be some middle ground c on the interval from A to B, such that this area, whether it's over a little bit and under on the opposite side, it counterbalances each other out. So it gives you that average area. So if you're looking at some sort of sales or production graph, maybe for this first half you're exceeding expectations, and the second half you are not. You're performing below expectations, but your net over that time period is right at expectation. All right, so that's what we're working on right over here. So in example 6, all right, we're going to apply this mean value theorem for integrals. All right, so we see our a and b are pi thirds and negative pi thirds. So I know that my function, right, my lower limit goes from pi thirds, negative pi thirds to pi thirds, cosine x dx is going to equal, I'm just going to write f of c for now, and then we're going to subtract our upper limit from our lower limit, and we know that that's going to create a 2 pi thirds. All right, so on the left side here, I can just integrate. So I know that the derivative of sine is cosine. So that tells me the antiderivative of cosine is sine. I'm just thinking about it backwards. It goes a little faster in my head. So sine of pi thirds is going to be radical 3 over 2. Subtract the sine of negative pi thirds is negative radical 3 over 2. All right, and then that is going to equal just radical 3, and that has to be equal to my right side of the equation, f of c, multiplied by 2 pi thirds. All right, so now I want to solve for c, so I got to isolate c, so I'm going to multiply by the reciprocal on both sides. So that gives me 3 radical 3 over 2 pi is equal to f of c. Well, I know f of c is really the cosine at c, so I want to know when does the cosine equal, it's a little bit of a ridiculous equation here, but 3 radical 3 over 2 pi. So this is my situation. So if this number ends up being a little cleaner, maybe this is a non-calculator question, but it is not. So in my calculator, in my y1, I would graph 3 radical 3 over 2 pi, and in my y2, I would be graphing the cosine of x. And I'm taking into account my interval here when I graph in the calculator here, negative pi thirds to pi thirds. All right, so I know that, right, cosine is going to be peaked at x of 0 there. So just estimating where my pi thirds are going to be, that's my bounds. And kind of ballparking this number here. So square root of 3 is about 1.7. So that means the numerator is about 4.5, and the bottom is about 6. So I know that this intersection is going to occur, right? This is going to be somewhere about 3/4 for that graph for y1, which is less than 1, which tells me I'm going to have 2 intersection points. All right, so in your calculator, type in that situation so you can solve, and based on this equation here, we are solving for c because they are asking for c in the direction, so don't give an x equals answer, you have to give a c equals answer. All right, and when you calculate all of that out, let's see, we should get, it's going to be a positive and a negative based on the symmetry, and 0.597057778. All right, keeping all the decimals. So based on the graph above, okay, so that tells me that this height C, right, is located at that 0.597 number. That's what gives me that height that's going to balance out any sort of over approximation and under approximation to make it that mean area. All right, so now we've seen success on both sides of this in the past of ways to remember this formula. There are advantages of knowing both. Just depends on what they give you. Just realize to move back and forth from one to the other, all you're doing is dividing by this quantity b minus a. So if you want it next to the integral symbol, you can just move it over. The advantage of that is if you're trying to solve for f of c and you want to do it faster, or if you have to deal with the integral and they give you a lot of information for f of c and b minus a. It's pretty interchangeable. You can do both. All right, example 7 here. Find the average value of the function. All right, so then that tells me that I'm looking for, I've got my integral then from 1/2 to 2 of x squared. I'm going to split it up right away because I see that I'm going to need to. Split that denominator, right, is equal to f of c multiplied by 2 minus 1/2. All right, value is a y coordinate, so in the end we're just trying to solve for f of c. So in that situation, we're going to be at an advantage if we can move this over and get f of c by itself. So this is really 3/2. So to move 3/2 to the other side, you multiply by the reciprocal. All right, and then I can take, I'm just going to write down my integral again. I'm going to try to clean up what I can. X squared over x squared is 1. So then that's going to be x to the negative 2 dx. All right, I want to make sure I close my bracket there for my multiplication of my 2/3. So I've got f of c already solved for, so now I've got to do my antiderivative. So 2/3 is going to be there. Antiderivative of 1 is x. Negative 2, go up 1 gives me to negative 1, and then divide by negative 1. And I'm going to evaluate that between 1/2 and 2. All right, so then I have my 2/3 is still there. So if I put my 2 in first, I've got 2 plus, that'd be a negative 1/2, minus, if I put my 1/2 in, I've got a half. So if you put a half in it, it's the negative 1, it's really a 2. All right, but with the negative there, right, it's going to be a negative 2. And all of this still equals f of c. So then I've got my 2/3 is equal to 3/2 minus a negative 3/2, right, plus the positive. So that's a 3, and the 3's can cancel. So then I've got 2 is equal to f of c. So my average height there is going to be a 2. So again, going back to that generic picture where we're going to be over and under a little bit here. So that means that that height that's going to balance it off for that generic rectangle is located at a 2. All right, find all x values in the interval that makes it equal to the average value. So that just means that we're solving for the value c now. All right, so that means I know that my 2 here is equal to f of c. Well, my function was x squared plus 1 over x squared, but if we're evaluating that at c, then I should be saying c squared plus 1 over c squared. All right, we're going to try to solve for c. So we probably want to do the same as we did before with my 1 plus 1 over c squared. So then if 2 is equal to 1 plus 1 over c squared, subtract 1 from both sides, right, cross multiply. So now I have my two x values. I understand it says x here. That's a generic input because there was a function of x. C is that specific x value that's located in the domain between A and B. All right, so there's average value. Here's the next part here, the second fundamental theorem of calculus. Sometimes this is called fundamental theorem of calculus part 2, depending on who's writing it down. So before we talked about if you take the antiderivative and evaluate between the upper limit and the lower limit, you subtract those to find the area under the curve. Now the second fundamental theorem of calculus deals with taking the derivative of an integral. All right, so they're generally called inverse operations here because they are going to undo each other. So you can see my integrand was f. After I take the antiderivative and evaluate and then take the derivative, you just get back to where you come from. All right, and that's going to be like with an asterisk there. You know, there's going to be a couple of caveats to that rule. All right, so we're going to go through that process here, and we're going to go through the long way and the short way so that you understand why it works. All right, so the directions just say find capital F prime. So if I'm doing that, I know that the derivative of capital F is just F prime. And now I've got to take the derivative of the other side. And some people will put a parentheses here, some people don't. It's personal preference on spacing. Okay, so if we do this one at a time and I just do the integral first, so then my antiderivative, that is currently t to the 1/4. So if I go up 1, I'm at 5/4 for the exponent. I can divide by 5/4 or multiply by 4/5. Then I would evaluate between x and 1. So that would give me 4/5 x to the 5/4 minus 4/5 1 to the 5/4. All right, so now that tells me that I still have my derivative here that I didn't take yet. So I'm looking to take the derivative of that answer. So now if I take the derivative using the power rule, I've got to bring my power down and multiply by my coefficient, and those are going to cancel out, and I'm going to have the coefficient of 1. Then I've got to take that x and go down 1 for the power. And this second term is a constant, so the derivative of a constant is going to be 0. So that tells me my capital F prime of x there is going to be x to the 1/4 or the 4th root of x, depending on which way you want to write it. All right, and based on our initial rule that we read, that if you take the derivative of the integral, they just switch over. So you're probably wondering why I took all that time to do that. All right, so now here's the shortcut and the checklist, as you may like to call it, to make sure that we are doing everything that we want to be doing. All right, so if you want to take the derivative, you're going to write down d of dx, and then your integral, and then your function, like all of that's going to be the same. So now, to make sure that everything is set up properly, all right, we need to have a constant as my lower limit, otherwise this technique doesn't work. You'd have to do it the long way every time. And you can note, even in above, right, we have a constant a as our lower limit. Like that's not just hidden there, like that's there on purpose. All right, the second part is going to be that we take the derivative with respect to x or whatever letter is appropriate. That same letter is in the upper limit. And of course, my integrand and my dummy variable are also talking to each other, but it's not the same letter as the other ones. They've got to be different letters. All right, and that has to do with when we went the long way here of my integration process. Like I can't use the same letter to replace that was already there. That's a conflicting variable situation. All right, so if this is all go, right, I got my lower limit is a number, my derivative and my upper limit are the same letter. These guys are all kosher. Then my rule then is to take this upper limit and replace that letter in the integrand. All right, and then the next step would be based on this upper limit. I'm going to take the chain rule of that upper limit. All right, in this situation, the derivative of that upper limit is a 1. So it's not necessary to do all this writing, but I want to make sure that we're aware of that for the next problem. All right, and we can see that it works out just fine. All right, the reason behind this lower limit being a constant has to do with this back procedure here. So when I take the derivative and there's only numbers there, that term goes to zero and it eliminates any sort of conflict of variables or adding up like terms. We know that's going to end up going to zero in the long run. All right, so let's try part B here. So if I take the derivative on the left, I have to take the derivative on the right. Okay, we'll do the same thing. We'll do one more long version here just to make sure it makes sense. All right, so then if I just want to take this antiderivative, 1 over t cubed would be like t to the negative 3 power. So if I have t to the negative 3 power and I wanted to take the antiderivative of that, I've got to go up 1, so that's t to the negative 2. I've got to divide by negative 2, and I need to evaluate from the upper and lower limits. All right, so I'm going to, now I'll leave it there because we have to do the derivative anyway. It's going to be nice to have it there. So that means I've got x squared to the negative 2 divided by negative 2 minus t, which is 2 raised to the negative 2 divided by negative 2. So now if I'm going to take the derivative of that, all right, so then in my exponent here, right, this is really a negative 4. So if I take the derivative, I got to bring down that negative 4. Right, so then I've got negative 4 multiplied by, with the negative 2 in the denominator, negative 4. So if I bring down a negative 4, then I've got to drop them down 1 power to a negative 5. My subtraction is still here. This back term is a constant, so the derivative of a constant is 0. All right, and that was the derivative, so I don't want to write this any further because I don't want to take the derivative twice. I took the derivative. So now I've got a positive 2 because negative 4 over negative 2. And then to make that positive exponent, I'm going to put x in the denominator. All right, so then that is my capital F prime of x. So now if we're going to go about this the shortcut way, F prime of x. Okay, so I'm double checking right here. So I've got my lower limit is a 2. I know I'm going to take a d dx here. So that x and the x squared and the upper limit match up. My t's are talking real nice to each other. So that means my rule is I'm going to take this x squared and replace that t just the way he is. So there's my t location, and that t location was cubed. And then I've got to chain it, right? So I've got my x squared chained as a 2x. So now my denominator power is a 6, but my numerator power is a 1. So that leaves me with 2 over x to the 5th. And you can see that they are identical. All right, so we'll work on part C here. So my f prime of x, I've got my constant down below. I know I'm going to take my derivative of this side. I've got my x squared. It's going to replace my theta. And then I've got to chain rule it. So just to make sure that that 2x is not associated with the argument of the sign, I just write it in front to make sure. And there we have part C. All right, so those are our two major topics for section B, the average value and the second fundamental theorem of calculus.